Okay. Nucleophilic aromatic substitution. So, in this sort of situation, what's going to happen is we're going to be looking at taking benzene that has a leaving group on it, and ideally an electron withdrawing group as well. We're going to see that that kind of two things are necessary for nucleophilic aromatic substitution to happen at kind of normal conditions. What this is going to look like is we will end up substituting at a position either ortho or para to our what's it called? Electron withdrawing group. So just like before, how we saw with electrophilic aromatic substitution that we had kind of nitro groups and other electron withdrawing groups were meta directors. It's the opposite here. So we're going to see that we're going to end up with nitro groups or other ketones or, whatever electron withdrawing things we have. We're going to end up getting our substituents to be either ortho or para to our what's it called? Electron withdrawing group. There we go. So note it's the opposite effect of the electrophilic aromatic substitution. Remember with EAS, we wanted our ring to be more negative because it's going to act as a nucleophile. With NAS, nucleophilic aromatic substitution, our ring is going to be acting as the electrophile here. So we wanted to have electron withdrawing groups on it. So we're going to see that we can go through this, and we'll see what's going to happen here. So here we go. Let's look at the mechanism. So what's actually going to happen here, I didn't draw the other one, but we would also need, we're going to see that it's going to take the place of the bromine. So if we want the bromine to be, or if we want our OH to be ortho, we're going to need it to be ortho to begin with. So here we go. Let's take a look at the ortho case. Here comes our dear friend, the nucleophile. So we're going to have hydroxide come in. It's going to go ahead and attack our brominated position. We're going to end up, as a result, doing all sorts of fun resonance. I better draw it at my NO2 as well then. Okay, all these lone pairs. There we go. So we're going to end up kicking out our bromine eventually, but let's go ahead and draw the resonance first. So this is why we need an electron withdrawing group, by the way, is for the resonance. Question?
Perfect.
Yeah.
Yeah, just quickly, I don't know if it's only mine, but your screen keeps coming in and out.
All right, let me try something. I'm going to... Oh, I see. I kind of have crappy internet right now. I see. Okay. I'm going to cut off the video. Maybe that'll help. I'm going to also try restarting the stream, so give me 1 sec. We'll go with that. Actually, okay. That should be better. Maybe? No, it's gone to yellow again. Okay, it keeps going. I see, Audrey, that it's going up and down, so I don't know what to do. I can restart my router, but then I'll be out for like 5 minutes, so...
Okay, no worries.
If anything, it's at least being recorded on my screen, so even if it's going to be kind of laggy or whatever, it'll still be there. So I'll maybe slow down or something a little bit, and we'll see. So anyway, so what's going to happen here is we're going to have our nucleophile come in, attack the position that has our leaving group. And so doing so, doing so. Oh my gosh, you're kidding me. I'm showing myself on Discord how silly. Wow. Okay, let's try this one more time. Oh yeah, I totally clicked the wrong window. Okay. Thank you, Eric. It's gonna be one of those days, it seems. All sorts of random silly things happening. Alright. All I've done, though, is the resonance. Alright, so we've got our bromine and our hydroxy group here. And now, all that's going to happen is we're going to end up closing our ring down. And we're going to end up kicking out our leaving group. So last time when we did electrophilic, we ended up needing a base, right, to come in and abstract the proton. That would end up getting our... that would end up restoring our aromaticity. In this case, what we're doing is we're kicking out a leaving group instead. So that's the difference here. Okay, and then doing that, we're going to end up with our product. And it's going to be the same case for para. I just felt like drawing ortho. It's the same thing for para. You'll still end up resonating to your electron withdrawing group. That's why you do need a strong or moderate deactivator to do these. Although for these reactions, they will actually activate the ring because these are the opposite processes from last time. So we end up losing our bromine. Of course, that's lost. That's as a leaving group there. So as long as you have any sort of leaving group, usually it's a halogen. You could probably have a tosylate on this. That would probably work. But if you're gonna if your point is to put an OH on there, it's kind of silly to tosylate it when you could just hydrolyze that instead of doing an NAS reaction. So that's what we're looking at here. All right, so it's a nice reaction. So if you have it as para, you get para. If you have it as ortho, you get ortho. If you have it as meta, you're not going to get a reaction to happen. Your leaving group, that is. If your leaving group is meta, you don't get a reaction to happen. And it's much the same reason. So the reason that we're allowed to do this is because the ortho and para positions will allow us to resonate onto the nitro group or our ketone or whatever. It'll allow us to show those electrons moving away from the site of attack. But with the nitro on a meta position relative to the bromine, then it's not going to work because you can't resonate it that way. If you try, it's just not going to work. So you'll end up putting a negative charge on the carbon instead, and so that's unfavorable. So it just doesn't happen as a result. Okay, so we need our electron withdrawing substituent to be either ortho or para to our leaving group. So first thing you need for an NAS reaction, you need a leaving group that is ortho or para to an electron withdrawing group capable of resonance. Actually, I've put these together in one, so this is what you need for nucleophilic aromatic substitution. You need a leaving group that is ortho-para to an electron withdrawing group that you can resonate to. So that would be something like a nitro group, a sulfonyl group. What else do we have? All of those are here. All these bits, oops. Any of these ketones or whatever, those can all resonate as well. So you need some sort of electron withdrawing group capable of resonance. Previously, we had kind of classified those as electron withdrawing substituents. You might be able to make the argument that you could also have protonated amines there. Those are strong deactivators we saw last time. That's probably enough to stabilize, but traditionally this reaction is done with resonatable, usually the nitro group, because the nitro group is probably our strongest electron withdrawing substituent, and it's very easy to put it on to a benzene ring, so that's typically the reason here. So this gives us like a lot of opportunity. So if we wanted to make this thing, starting at benzene, wow, that's ugly benzene. OH group we can't put on directly. We don't have an electrophilic aromatic way of putting on a hydroxy group. We're going to see that for us, the best way to do it is to put it on as a nucleophile using nucleophilic aromatic substitution. And so, a good thing for us is that our typical leaving groups are orthopara directors, right? Our halogens and so if we have bromobenzene or something, or if we put on a halogen onto our benzene, that would direct a nitro group para to it, right? So we have this advantage because now that we have a nitro group para, then we can go ahead and kick out our halogen. So the halogen will guide our electron withdrawing group para to itself, and then we can go ahead and mess with that later. So this is a good thing. So because remember, we want it para if we want to do nucleophilic aromatic substitution. So easy enough to put on a halogen, right? We just need to go ahead and take our benzene. Let's put it with some bromine and the Lewis acid. This is an electrophilic aromatic substitution. We end up putting our bromine on. Great. So with this now, we can go ahead and continue. If we go ahead and put a nitro group on, chances are that nitro group is going to go para, right? Para positions are favored. That is your preferred product. You might also get some ortho, but that would be fairly easy to separate out if that was a byproduct you had. Just thinking like kind of practically speaking, if you did get the ortho one is much more polar than this para one is. So it's pretty easy to separate. TLC, a column, whatever, that would easily get out any accidental ortho you have. But since para is the preferred position, I'm just going to go ahead and put that as our main product. And so now we can say, aha, now that we have this, we can put on our OH group. So we can kick out our bromine. We'll end up with our hydroxylated one. So we have this advantage here in that halogens are orthopara directors. And if we want to do a nucleophilic substitution, we need a para or ortho nitro or some other electron withdrawing group. So we can use the halogen to put on that group and then kick it off. And it's already in the position it needs to be in. So it's a useful synthetic technique. And now we have a strong activator. We can do whatever. Now we can put some stuff on ortho or whatever we need to do. So we're good with that. So, cool. I guess technically also with this we would need, because we have this OH, we're gonna need step 2 some sort of acid wash just to put on the proton, because putting an OH on it would be, wait, no. OH would be okay. Never mind. We're good. I'm just so used to putting a base, we need to do an acid later. So, no, we're good there. So you can do this with a lot of different nucleophiles. So stronger nucleophiles are ideal for this. So strong nucleophiles, remember that's like hydroxide, alkoxides. I don't know, what else do we want? I guess I should put these minus charges on their actual oxygens, but what else do we have? Sulfides, nitriles. Really, your strong nucleophiles, remember these just localized negative charges on atoms. They're very good for this sort of reaction. Amides. So, fun stuff. So if we do want this, notice if we want the NO2 and an amine on there, remember that we can't nitrate something that has an amine on it. But we can use it as a nucleophile and kick out the bromine. So remember last time I told you, if you have an amine on your benzene and you try to nitrate it, you're going to end up with a mess, because the conditions for nitration will also react the amine group. So this way, if you do put the nitro on first, then you can substitute in the amine nucleophilically instead. So lots of interesting things you can do with these. All right. Mm-hmm. What about it? Oh, is it just one of the rules? Yeah. Yeah. So it's understood that if you have aniline or some substituted aniline, you cannot nitrate it, because it will end up destroying your amine, and you'll get all sorts of weird stuff happening. You'll get weird polymerizations and all that. So, okay. I want to look at the idea of the resonance again. I drew it all in one step here, where we just resonate directly to the nitro group. Technically, you don't have to. I'm going to introduce this so I can say I introduced it. I'm cool if you do the resonance all in one step. So if you do your mechanism exactly like this, where you have your nucleophile attacking and things resonate away towards your electron withdrawing group, and then you close it down later, kick out your leaving group, I'm great. But I think technically I have to teach you the resonance. So I'm going to do that just one more time. So let's say we have... Actually, this is a bad one because it's pretty... let's just do the nitro. Or no, we'll do this. There we go. Slightly different. Why not? Let's put on a different nucleophile too. We'll pretend this is a different reaction. So, technically, if you wanted to be super correct about this, first step would be you attack your benzene with your nucleophile, and you end up kicking your electrons onto a carbon. I'm going to just draw the resonance here. Actually, no, this is not resonance. This is an actual reaction. Now we can have resonance. Okay. Technically, all this can resonate. Can go here, and now we go here. And we can resonate onto the 3 positions on the benzene. So now we'll have our lone pair here. Ideally, we would resonate it towards that sulfonyl, but in the interest of showing you all this fun stuff, I have a name for this. Do you remember last time we talked about the sigma complex with the electrophilic aromatic substitution? Sorry that we have to go down here a little bit. I'll adjust it in just a second. Okay, I'm gonna switch it to the side so we can see all of them. This is technically called a Meisenheimer complex. I don't care if you know that. I don't care if you do it like this. I think, honestly, this is silly, because all of these resonances are not very good. You have a resonatable electron withdrawing group, why would you not? But because someone spent the time to discover this, we have to give them a fancy name. So there we have it. So I'm okay if we don't do this. If you just resonate all around, go right ahead. I don't need you to understand this as much as I need you to understand the resonance aspect going to the actual electron withdrawing group. All right, so again, I am just fine if you use your mechanism like this. All right, so attack it, resonate directly to your electron withdrawing group. Next step, resonate it right back down again, and kick out your leaving group, and you're done. I am happy with that. I don't need you to show me all the resonance. The sigma complex, I might ask you. The Meisenheimer, I'm not going to ask you. All right, so I'm going to be very clear about that. Okay, so you don't have to worry about Meisenheimer. Okay. Oh my god, I have a green connection for once. Hopefully that's... Oh, no, it wrecked red. It's interesting. My internet is just playing tricks on us today. So, who knows? All right. Any questions on the nucleophilic aromatic substitution? So, remember, two things are needed. You need a leaving group. You also need a strong electron withdrawing group somewhere either ortho or para to your leaving group. So you'll end up replacing your leaving group in the location that it was, as long as you have that electron withdrawing group either ortho or para to where it is. Okay, so that's what you need for nucleophilic aromatic substitution. The last thing we're going to talk about is called elimination addition. And here, this is going to be a leaving group without a strong electron withdrawing group orthopara to that leaving group. So we're going to see here that the elimination addition reaction requires a lot of heat and pressure. Because without that kind of favorable resonance, we're going to have to really crank things on at this. So we're going to see that if we just tried this normally, we don't get a reaction to happen. Because we don't have that electron withdrawing group to stabilize the Meisenheimer complex. However, we can do this if we crank the temperature up to 350 degrees. Not a problem. We go super crazy with it, and we'll end up getting our product. Ta-da! So you don't technically need the electron withdrawing group. but you see here the conditions are quite inhospitable. 350 degrees, like that's quite hot, right? We're talking like hotter than most gas ovens can go, right? It's pretty high of a temperature. What is that, like 800 some odd Fahrenheit? So pizza oven temperatures are required for this. So as you can imagine, that's going to be pretty tough because without the pressure there, things are just going to vaporize and do who knows what. So you also need high pressure to keep things liquid. And so, tough reaction to do. But we have some interesting things that happen with this. We might expect that if we put something else on it, we probably wouldn't change much. But if we go ahead and do this, what's interesting is we actually get two products out. So you might be thinking, well, what the heck? Let's see what those products are. So first one is product we expect, right? Substituting our chlorine out, and now we have our hydroxy group. But we also get this. And it's even weirder. We get it also on a meta position. Or not necessarily a meta position, but a position adjacent to where our leaving group was. So the methyl group there is not actually participating in the reaction. It's there just to illustrate that we don't actually necessarily replace the chlorine directly. And so that's going to give us some insight into this mechanism, because we're going to look at the mechanism as why this happens. Excuse me. So this one, it's this one's in the same position as the chlorine was, right? But here we have the OH one spot over. And so we have some interesting things happening. So let's look at the mechanism. Let's see why this is happening. Though, I just want to check in right now. How is our quality? I can try reducing the frame rate a little bit. That might help. How are we doing with that? Is it still crappy?
No, it's good.
It's good? Okay.
Your voice is kind of, I don't know if it's for me or others, but it's kind of jittery.
Okay, well. I hope, yeah, I understand that might be the case. Let me see if I can adjust the, I'm going to try changing the quality. I'm going to reduce the resolution and frame rate a little bit. That might help. So it may be a little uglier now, but maybe that'll help with this. Okay. So let's go ahead and see what's going to happen. And so if we want to do this, what actually is happening here... This reaction was actually discovered using amide as the nucleophile. So I'm going to draw the mechanism in terms of the amide. So even if you don't have that methyl group on there, they did do this isotopically labeling the carbon that was on the chlorine, and they found that some of the times you'd have your amine on it and sometimes not. So this is the weird part that happens. So let's take, we're going to use amide as our nucleophile this time for the mechanism. And we're going to take a look at what happens here. So here we go. We make something strange. So normal proton abstraction. Remember that sp2 carbons are a little bit better at accommodating a negative charge than sp3 carbons are. So vinyl hydrogens are a little bit more acidic than plain old aliphatic ones. So we now have this negatively charged business, and I chose the amide because it's a stronger base. So it's just going to make this a little bit easier to understand, I think. So with this, what happens now, oops, I lost a chlorine. Minus 10 points for me. Okay, here we go. Here we go. So what's going to actually happen is you're effectively eliminating in 2 steps your chlorine and an adjacent hydrogen, and you get something very bizarre. You get a triple bond in your benzene, which, as you can imagine, is quite unstable, right? The geometry of a triple bond should be 180 degrees, right? Because those orbitals need to overlap properly. But, by the way, this is called benzyne. So benzene, alkenes, benzyne has the alkyne in it. Benzyne is terribly unstable. It's terribly unstable, but we know it exists. And how we know that is actually through a Diels-Alder reaction. If you throw cyclopentadiene with this, you can actually capture the benzyne. So it's quite interesting that we have evidence that this is the intermediate that we have here. So I'm going to draw it super obviously here, but if we have cyclopentadiene, you actually get a Diels-Alder reaction between them. Wait, hold up. That's totally wrong. There we go. Oh, and there we go. So this one actually has to attack that side. There we go. Okay. What's interesting is you actually get the you get a benzene as your the last bit here. So there's evidence that this happens. So this can be isolated, right? This is not an unstable compound, this Diels-Alder adduct, but the benzyne is. And we remember that we could react alkynes as dienophiles, and so there is evidence that this is the intermediate here. So it's weird. Anyway, so because of this weird overlap of the orbitals, normally to make a triple bond you need a set of p orbitals that are vertical, a set of p orbitals that are horizontal, 90 degrees apart that are overlapping. But you can't do that with the benzyne because you have your orbitals are working in different ways, and you don't have you don't really have truly sp carbons here. There's still going to be sp2. So you're not really having p orbital overlap, you're having sp2 orbital overlap, which is a little bit weaker. And so it's you get some weird stuff happening. Suffice it to say, it's unstable. And therefore, we can go ahead and react it. So let's go ahead and take a look at our benzyne. And I'm going to put it back up at that carbon because that's where I had it in our mechanism. Here comes our dear friend. Actually, probably it would be another amide ion. Be a little bit better of a nucleophile. Here we go. Option 1. We can go ahead and attack that carbon. Option 2. Option 2 is we attack the other carbon. So I'm going to just do this one in purple because I'm doing two different mechanisms. Or well, it's the same mechanism, but this is why we get our nucleophile on different sides of where that was. So the top carbon there is where the chlorine was, right? And so the purple mechanism would be the one that leads us to having it, the amine, where the chlorine was. The blue arrows will show us the one that gives it to the adjacent position. All right, and so if we move these forward, we end up with an anion again. And then we just need to go ahead and take our dear friend the ammonia, which we produced in one of the last steps. And we're just going to have our benzene act as the base. It's going to go ahead and just steal a proton. Same thing here. We end up making some more amide, so we still need one equivalent of the amide ion in here for this reaction, but typically you'll use ammonia as your solvent anyway. You'll use the conjugate base, conjugate acid rather, and you'll end up with your product. So for right now, of course, these are identical because we have nothing else on them, but if we had that methyl group at the bottom, you would see indeed that you get two products here. And there's a 50-50 relationship. So, because you can attack your benzyne from either side. So it's weird. So first thing you do is you eliminate. You get rid of your leaving group along with a proton. That's what elimination is, right? When we talked about eliminating to make an alkene, E2 and E1 reactions. It's the same thing, right? We eliminate by kicking out our leaving group and removing a proton at the same time. So we get our benzyne intermediate. That benzyne is symmetric. There's no reason that our nucleophile would choose to attack one or the other. And so as a result, you get 50-50 ratio here. So 50-50. All right, so with this, with elimination addition, you do have the possibility of ending up with multiple products if you have a disubstituted or more benzene. If you just have one leaving group on it, it doesn't matter because these two products here are identical, right? There's no difference. They're both aniline. That's it. There's no difference between them. But if we did have a methyl group on there, we would see that we would get different compounds out. All right, so that's the case of elimination addition. So elimination addition it uses kind of high temperature, pressure to do a nucleophilic aromatic substitution without an electron withdrawing group on the ring. This is probably the least likely one you'll use, synthetically speaking, but it is an option. So that's why it's part of the curriculum. Is even though it's a little bit less useful because you do end up with the mixture of products, it is just another tool you can use, even if you don't end up using it. So I'm going to make it vertical for a sec so we can do that. So this middle Diels-Alder reaction, you don't need to worry about that either. This was just showing you our evidence that this is the intermediate. So and we could have just said we have, I don't know what, but all these reaction mechanisms we talk about, we have evidence to support them. So the evidence that we have this Benzyne thing, even we cannot isolate Benzyne, but we can isolate the Diels-Alder product of Benzyne with a diene. So that's our evidence. You do not need to know that, but I think it's pretty cool. So, but I do want you to know the mechanism. So first step, eliminate, make your Benzyne. Second step, add to it, and then protonate. So deprotonate first step, protonate last step. It's your standard base catalyzed reaction, right? So there we have it. Any questions on that one? All right. So, did Chalmers do any like practice with synthesis with you guys yet? Or has he like indicated like on Thursday if you're gonna do that, or are we gonna be doing that here? If you have any idea.
We did not nucleophilic.
Electrophilic ones?
Yeah.
Okay. Well, let's do then just a couple here. I'm gonna look in the back of my book here, and I'm gonna find some good ones for us to do. And we're gonna make some nice products here. All right, let's do this. Starting with benzene. These are all yeah, we'll do it. Okay. Okay. Let's do a few. These are a bit hard to make up because we run into the risk of not being able to do it. So I'm going to steal some from the book. Plenty of questions there. So let's do this one. Alrighty. What the heck are we going to do here? Oh, you know what? I switched two things. Hold up. That'll make it a little easier on us. So, I don't know Chalmers' approach to this, but my approach is let's first figure out how we can even put on all of these functional groups. I think that's the best way to go about doing something like this. So, if we want to put this thing on, do we remember how to do that? Perhaps we do. Friedel-Crafts, maybe Clemenson. Depending what we do. Depending, we may choose to do alkylation, just depending on what we have on our ring. Could save us some steps if we do something like that. Or we can do an acylation and then Clemenson, that's fine too. And then cleavage, right? Oxidative cleavage. Nitro group we know how to put on. Right, that is just nitration. Standard. Chlorine we know how to put on. What color are we doing for chlorine? Dark blue. Okay, sounds good. Some sort of Lewis acid and chlorine. We'll get that on, right? And then hydroxide, that's one we've learned today, which we'll do in, let's use the less used kind of foresty green here. This we need a leaving group to do NAS with. Or technically we could Nah, we can't do eliminate. I mean, depending the order we do things, we could potentially use elimination addition, but let's just avoid that. we have 2 electron withdrawing groups on this ring, so it'll be good to do nucleophilic aromatic substitution as a result. Because as we see here, that OH is ortho to a nitro, and it's also para to a carboxy. So we're in a good place to do nucleophilic aromatic substitution there. But in order to do that, we need a leaving group there first. So now that we've looked at these, what are we thinking? What should we do first here?
The one that has the highest or the strong activator.
Strongest activator, okay. Which one do you think that's going to be? One of them. Indeed, that's correct. 100%. Very good.
Is it the NO2?
NO2 is the worst one, actually. That is a strongest deactivator. However, we're going to need that NO2 to get that OH on there, for sure. Absolutely. That's the strongest for nucleophilic substitution. But generally, we can't just start... Since we're starting with benzene, we have to do some electrophilic aromatic substitution first. So, no luck with NAS right off the bat. And so we could put the NO2 on first. But I would say, yeah, we should probably put the top part on first. The reason for that is because before that OH is there, that's going to be a bromine or an iodine or something that's a better leaving group than chlorine, right? Although we don't really have to worry because the chlorine is meta to our electron withdrawing groups. So even if it's just a bromine, we'll be okay. Even if it's just a chlorine, we'll be okay, probably. Because of the location of where it is. So, because the OH is going to be a chlorine, the other... everything else here is electron withdrawing. They're all deactivators. Eric, you did have the right idea to do an activating group first. And so what we might do with that is do our Friedel-Crafts and Clemenson. So just have it as a methyl group or an ethyl group or something, where we have some sort of electron donating group in there. And then we can start messing with things. All right, let's do it. So, probably a good place to start is, in general, yeah, some sort of activating group. So, if we take benzene, what would we like to put on it? Remember that our Friedel-Crafts, we can use really any alkane, or acyl chloride rather, that we want. Why not just, let's just use acetyl chloride, who cares? Step 1, step 2, we'll do our Clemenson, we'll just do it right away. Because otherwise we'll have a withdrawing group. If we do that, we get something ugly. Nope, let's try this again. Ta-da! Lost a carbon, there we go. We have ethylbenzene now. Now what should we do? If we cleave it, then it becomes a meta director, right? And then, I mean, it's not... We do want positions meta to it, but as soon as we make that meta thing, we have no way of going back. So I would say that we should probably put on something on the para position first, before we make it into a meta director. So what do we want to do?
Leaving group.
Let's put our leaving group on there. Okay, what leaving group would you like? Narek, it's your choice.
Bromine.
Bromine, very good. Okay, so let's put a bromine on. So let's put some bromine on here. Again, chances are it's probably going to go para, so we're good. That'll be the most likely product. If we wanted to be sure, we could have used isopropyl. Oh, no, we couldn't because acyl. I think we can't do that, so we're good. Okay. Now what?
Can we start with the leaving group to the nucleophilic?
If we heat the crap out of it, we would end up having to do an addition elimination. So because we don't have an electron withdrawing group that can resonate right now, we can't do the regular NAS. We would have to do elimination addition, and then we would end up having two products.
Can we stick the chlorine on this?
All right. If we do that, however, let's do it. Cl2, AlCl3. Here's our chlorine. Uh-oh. Why'd the chlorine go there?
It's meta.
Neither of these are meta-directors. Ethyl group, bromine are both ortho-para-directors, right? But the stronger activating group is the ethyl group, so it's going to go ortho to the ethyl group, which is not where we want it, right? We want it ortho to the leaving group. Right? Make sense? Does that make sense?
I forgot the strongest one was.
Strongest one determines it. Yeah, it'll lead us where we need to go. So that's, I mean, this process, there is some guess and check. I don't want to say guess and check, trial and error. There we go. That would be a better way of saying it. So, where you try things, you have to think, oh wait, no. If I try and chlorine it now, it's going to go in the wrong spot. So, the problem with that is these two positions are, the two positions we still need are ortho to the bromine. But our methyl group is going to be end up being the director here. So, how do we change that?
So with NO2, it's a strong deactivator. Would be meta to it. So we have to stick
No. So it's always what's on there that directs it. So nitro is a meta director, you're correct. But that only directs things if nitro's already on the ring. So your current substituents on your ring will direct new substituents. So we're looking at the bromine and the ethyl group. And again, right now the ethyl is the stronger activator between the two. So ethyl is going to determine where things go. I like this discussion. We're seeing a lot of why things won't work, which is very important. So I'll give us a little hint here. So,
Question?
yeah, go ahead.
Oh, I don't know.
You sure?
Yeah.
All right. So let's look at it. So we have this ethyl group and the bromine on there. If we do any sort of electrophilic aromatic substitution, it's going to go ortho to the ethyl group. So we need to get rid of that ethyl group, right? Because it's going to direct all of our new substituents, and we don't want it to. So let's get rid of it. How do we get rid of that ethyl group? Is there a way we can make it so that bromine becomes the director? The most activating. I'll give us a hint.
Do we fully go through with it?
Yeah, go through with it. Cleave it off. If we do this, now this guy here, moderate deactivator. This one's a weak deactivator. I'm sorry, wrong letter. The strongest activator always wins. So between these two, the closer one to an activator is the bromine, right? As odd as it may seem, they're both deactivators, but we see here that our between those two, bromine is better at activating because it's less good at deactivating, if that makes sense. So remember, it's kind of, this is the order of activating things. So strong activators are our most activating, strong deactivators are our least activating. So comparing these two, a weak deactivator is better than a moderate deactivator in terms of directing where things are going to go. And bromine is still an orthopara director. Right? Remember that these guys are orthopara directors. These ones are meta. So currently now, our bromine is going to dictate where things go. That is our strongest activator right now. So, what may we want to do?
We just add the chlorine now, and then the NO2.
In which order?
Chlorine first.
Chlorine first. So, that may pose a problem. Because chlorine, if we put the chlorine on...
Oh, it's a weak deactivator.
It's a weak deactivator, right? So we're going to have a competitor for our thing. Yeah, so I'm glad you noticed that. So, I don't know why it's purple, but apparently, then we have now, if we try to nitrate this, we don't know if we're going to end up here or here. Because both of those are weak deactivators. I mean, bromine might be slightly better, but like that's a tough call, right? There's not a very clear distinction about what's better here. So I would not put the chlorine on next. So therefore, our option is put the nitro on. Alternatively, if we want, we could probably do the nucleophilic one. Remember that we have options here. There's often many ways to go. We can go ahead and stick the OH on now because we have an electron withdrawing group para to our leaving group, or we can put the nitro group on because we still have the director there. In either case, we're going to get our product. So we have multiple ways to go here. So let's go ahead and put our nitro on. This poor benzene is going to be so deactivated now at this point. And again, symmetry, it doesn't matter which ortho position we put our nitro group on. I'm going to just put it where it is on the one that we've drawn here, just because, remember, because they're symmetrical. We could put it either spot, so we're good there. All right, now what do we want to do? I would say, yes, we could chlorinate. If we could, it would go to our position ortho to the bromine, the other one, which is where we want it. But this poor ring now has 3 deactivators on it. It would be probably pretty tough to get this benzene to do any more electrophilic reactions as it is. I can't say this is a hard and fast rule of thumb, but remember, we want to kind of keep activators on as long as possible. We now have 3 deactivators on our benzene. Things are going to become really tough to make them happen. So I think at this point, we should probably put our OH on there. If we didn't do it in the last step, let's do it now, before we put the chlorine. OH is still an orthopara director, so it's still going to put the chlorine in the right spot, so we don't have to worry about that, but now we just have to consider, like, look at all these deactivators. Like, let's fix this situation. We're now in kind of the best possible place to have NAS happen anyway. So, let's do it. With this one, by the way, we probably will need at least 2 equivalents of NaOH. Why? Why do we need 2 equivalents?
Because it makes 2 products, or...
Not quite. Well, I mean, you're not wrong, but I think the way that you're thinking about it, the 2 products you're thinking of are wrong, but yes, you would get 2 products, but Actually, you probably still only get one product, and it's the wrong product. Why? If we only put one equivalent, why are we going to get the wrong product? What is NaOH? Besides a nucleophile. What did we use NaOH for in Gen Chem?
It's like a base.
It's a base, right? Notice we have a carboxylic acid on this molecule.
Take the
It's going to take the proton first. So that's the first step. Is it's going to go ahead and just attack acid base style, make water, and go do its thing. And once all those are reactive, then we can go ahead and do our substitution. So just, it's always important that we still keep these things in mind. NaOH is very cheap, whatever. Go ahead and throw 2 equivalents there, 2.5, whatever, excess. But at least 2 equivalents, because we have to make sure that we are going to end up getting our carboxylic acid that's going to react first, right? So we probably will also need then some sort of like acid wash to regenerate our carboxylic acid, right? Otherwise we'll have the carboxylate salt. So isn't that fun? You thought you could just get away with doing these sorts of reactions? Nope. You still have other ones to deal with. So that's going to end up now putting our hydroxy group on. Awesome. If we wanted, we could have made the carboxylic acid into an ester and then cleaved it off later, but probably just easier to use excess NaOH, right? Like, don't even worry about it. So, all right, and then last step, chlorinate. You probably, I don't know if you would need the Lewis acid. I would put it in just in case. We have a strong activator, but we also have strong deactivator. So probably a good idea to put that Lewis acid in there anyway. Even if you have a strong activator and put your Lewis acid, I'm cool with that. If you always put your Lewis acid, I'm good. However, if you have a strong activator and don't, I'm not going to dock you because that'll work. So, ta-da, we did it. So,
Question?
yeah.
I have a quick question.
Mm-hmm.
When we add the NaOH, how come we don't put heat with that one?
We probably, but because we have the nitro group, we don't really need heat with it.
Oh, okay.
We also have the carboxylic acid. We have 2 good deactivators on there, so we should be okay without heat. If you put heat, I'm not going to dock it. Like, that's fine. There's like some reactions you are forced to use heat, right? Like you don't. I don't know what. Like this one, you needed 350 degrees or whatever to make it happen. If you just write heat pressure, I'm good. You don't have to put an exact temperature or anything. But this one, you have to put heat, like an absurd amount. Like these other ones, I don't know. You might need some slight heat, bring them up to 50 degrees or something. But like, I'm not going to worry about that. So, okay.
Another weird question.
Yeah.
So when you ask put the H plus H2O, can we just put H3?
Yeah, that's fine.
Okay.
Just fine. Mm-hmm. So I'm just putting it vertically so we can see all of this stuff here. So that was our goal, right? Was to make this tetra substituted thing. And so, yeah. What I will do is I'll raid Mrs. O's SIs, because she has, I think, like 500 or some crazy amount of practice problems on these. I don't know if she has the key for them, but she has spent a long time making these sorts of things, so we'll steal hers. Because the book, it's got some, right? But it's got less interesting ones, I think. Like none of these so far have we needed to put the sulfhydryl as or sulfonyl as a blocking group. So, yeah. Alrighty. Any questions on this? This one. Alrighty. Yep.
Can we do another one? Like this?
Very well. Okay. let's see here. I'm going to just make one up. We'll see if it works or not. If it doesn't work, I'll change it. So we'll make it work. All right, here we go. I want us to go from benzene to that'll be fun. How are we going to do that? What do I want down here? Yes. Okay. Yeah. First step. How can we put all these on? One of them should be relatively straightforward. The other two maybe not so much. What's the easiest of these to put on? NH2, right. That one we do know. So we nitrate and then reduce. The ester in the middle there, similar to what we did last time, but do you remember how to make esters? Back in chapter, I don't know, 11 or 12, did you talk about esters? I think you did, right? You did the banana oil stuff.
We didn't do that experiment,
But you remember?
yeah, we go from like a carboxylic acid.
Yes, right, exactly. Yep, so carboxylic acid and alcohol will give you an ester. So we know how to make carboxylic acid. That's going to be Friedel-Crafts, Clemenson, and then cleavage, right? That'll give us our carboxylic acid, which we can then combine with an alcohol to make our ester. Fluorine. How do we put a fluorine on a group? Can't use F2, right? We don't typically do that.
I was gonna say F2, but
Indeed. This is how. We're going to have to use F minus, current average of this class. Oh, that reminds me, I need to talk about that. We're going to have to use F minus in a leaving group. That'll be how we put this on. So we'll use that nucleophilically. So remember, halides are pretty good nucleophiles, right? So we can use F minus as a nucleophile here to replace a leaving group. So with regards to the exam, by the way, I have decided what I'm going to do. And I think you'll like it. So I think 7 of you talk to me, of the ones who did come forward. What I'm going to do right now is I'm going to give you a 0. However, if 2 conditions are met by the end of the semester, I will replace that 0 with your final exam score. So, first condition is I find absolutely no evidence whatsoever of cheating for the rest of the semester. That's condition 1. Condition 2 is at the end of the semester, the 7 of us, 8 of us, because I'm a person, I suppose, 8 of us are going to come together, and we are going to come up with a kind of set of guidelines for future students. We're going to come up with what qualifies as academic dishonesty and what doesn't, to make it very clear for future students, so I can give this to them and say, here's all the things you can't do. And so you guys are better cheaters than I am, so presumably you'll have some thoughts. And so that's what we're going to do. All right, so again, 0 for right now. If these two conditions are met, first condition, no evidence of cheating for the rest of the semester. Second condition, we come up with guidelines together later on. Then, after the final exam, you message me, hey, I'm one of the people who cheated on the first exam. Can I get my score replaced? And then I say, why, yes, of course you can. All right? So, any questions on that? I know, obviously, I'm not going to have you, out yourselves to the class here, but that's the thing. I'll send it out in an email as well, so you'll have it in writing. And then if there's any confusion on it, you can let me know. Okay? That's the plan for that. All right, let's go ahead and do the synthesis. So, what the heck do we do first?
Same thing as strongest activator.
Strongest activator first, okay? What's our strongest activator?
The right side, sorry, I'm blanking out. We tried
Which color?
fetal crab.
Okay, so you want to put an alkane on it. Okay. That's not our strongest activator, but I like that. I think that's the best place to go, actually. Our strongest activator would be the amine, right? But if we put the amine on, we're going to have trouble trying to get a fluorine or some leaving group there. If we put the amine on, right? We're going to have trouble putting something on a meta position. So, I agree. Let's start with Friedel Crafts. But there we go. Oh, what am I doing? So let's do it. Let's do our acetyl chloride again. It's kind of ugly. And we can reduce it.
So we always do that step first?
No. But it just so happens that this happens to be the best step to do first. So, yeah, I don't want to make it seem as though that's always a good idea, but you typically want... The first step should be to put an activator on if you have that option. So, there we go. Okay. So, if we do that, I'm going to put it... Oops. Right here. Our ethylbenzene. Now what?
We have the choice of putting an NH2.
All right. How do we do that?
Just do it.
Just do it, he says. Wow. What do we have here? More zinc and HCl. No, NaOH. Oops. All right. Perfect. We have our amine on now. Uh-oh.
Question: are they both strong activating groups?
They are.
So does that mean we can't do the NH2?
No, not at all. You could definitely put more activating groups.
Ah,
Do you put the fluorine on and then later cleave off?
Hold up. Is this getting what I've drawn here? Does this get us to where we want to go?
No, because it's in the
It's the wrong spot, yeah. So I would not do this step next. Because we end up with our amine para, right? Para is the preferred position. So what do we do? And that's why I like these, is because there's a lot of trial and error. So you not only get very familiar with all these reactions, but it makes you look and be like, oh crap, this is going to end up putting it para. So what do we do instead? Remember, what's that? Okay, so in order to put the fluorine, we have to put a bromine or some other leaving group, right? So if we do that, instead we're going to get bromine over there. It's not where we want our bromine, right?
Isn't it ortho and para?
Yeah, but para is always the preferred one.
Oh, yeah.
So remember, we always will draw kind of the major product. So yeah, you would get some ortho for sure. But we would rather have it where it's only one of them.
We do sulfonation and then desulfonation.
Aha! Yes, very good. I have to turn around a sec because the dogs are being cute. Okay. Very good. Yes, absolutely. We're going to block off that para position. We are going to make it so nothing can go there. Awesome. So, now we can do all these other things that we wanted to do, because now we have blocked off our para position with a blocking group. And remember, we can remove this. Remember, dilute sulfuric acid will take this thing off. And since our final product, everything's all clustered up, right? So we're definitely going to need some sort of blocking group to prevent that para position from being attacked by something. So, cool. Now, which one do we want to do? Do we want to put the amine on, or do we want to put the bromine on? And there are choices to make here. So let me actually go up here. So if we put the amine on, what's going to happen? If we put the amine on, it becomes the strongest activator. Right? We could leave it as the nitro. That would be okay for now. If we leave it as the nitro group, then it won't take over. Or we could put on the bromine, either way. So we could either nitrate or brominate at this point. Either one of those. But I would not go all the way to the amine, because at that point now our amine becomes the strongest activator, and so the amine is going to start telling, we can't put the bromine on after we put the amine on. So, does that make sense?
Yeah.
Can't make it the amine yet. Cool. So, in the choice, because we're going to have to put the bromine and the nitro group on, let's put the bromine on first, because it's less deactivating. Again, just something to keep thinking of is, we don't want too many deactivators in there. So as long as we can hold off on, we want to keep our activators on and put our deactivators on later. These are just things to keep in mind, because we want our benzene to be as reactive as possible. So let's put the bromine on first. Last time I used aluminum, so this time I'm going to use iron. It don't matter. And because we have the choice symmetrically, it's fine to put it on either spot. I'm going to put it where we want our fluorine to be. And there's another reason why we shouldn't have nitrated this yet. Alright, so let's do it. But what's going to happen now? What do we want to do?
Say we can put the nitrate group.
We can. Well, I would say we can't leave it as a nitro. Because if we leave it as nitro, we're going to have problems because, I mean, it's not really a problem, but the nitro as an electron withdrawing group, it's going to be meta to our bromine, right? We would rather have something orthopara to our bromine to get it to leave.
Just a quick question. Sorry to ask this, but what's the strongest activator right now?
Right now, the ethyl group. Yes. I mean, what's sorry about asking that? That's totally a legit question. So,
Because I got confused about the bromine.
yeah, bromine is a weak deactivator, and ethyl is a weak activator. So yeah, it would definitely be a good idea to have like a chart of these or something when you're working on these. Be like, what the hell are all these groups? So, what do we want to do? Again, here we have options. There's not really a right or wrong way.
Add the fluorine.
We can't add the fluorine yet.
Can I say we could desulfate, but that'd be later?
Correct. We want to put on our other group first. Because we still need our ethyl group 2 to tell us where to go. So I think nitrating would probably be our best bet. Or not nitrating, putting the amine on. So doing the nitric acid and the what is it? The iron and HCl, and then the NaOH. That'll get us to having our amine. And it'll be ortho to our thing. Although we may want to hold off on doing steps 2 and 3. We may want to leave this as nitro. It's again, there's options here. You could leave it as nitro. That'll probably help out the fluorination part. Or we can just put it as the amine. These are like more subtleties. Like I'm okay with either one. If we leave it as nitro, that's good because then we are still withdrawing electron density, making it more nucleophilic, but we still need something in the ortho position from the bromine in order to make this nucleophilic thing happen. And so what we might do now, since we're out of time, let's cleave off. Remember that the carboxylic acid, NH2. The carboxylic acid is something that we can use for NAS, right? It's going to be, I don't have my sulfur on there, SO3H. If we go ahead and do this, we can put our sodium fluoride in. I know we're out of time. Go away. NaF. Maybe. Here we go. We've got our fluorine now. And look at this. Here we go. Ethanol and some dilute sulfuric acid. Remember, we need an acid catalyst to get this to happen, the esterification. And if we use sulfuric acid that's dilute, we'll also take off our sulfur. And boom, we're done. I mean, we'll probably have NH3, but whatever. Who cares? We can just deprotonate that later. So, cool. Hooray! We did it. So, great job. See you on Monday. We'll go from there. All right? See you later.
Thank you.
Uh-huh.